Hey everyone, it's me again. I'm back, page 4 of the gases outline for AP. We're going to be talking about Jacques Charles, okay, the inventor of hot air ballooning, well, at least one of the guys involved in inventing hot air ballooning. And we're going to be able to actually start to look at the ideas that allowed us to measure absolute zero for the first time. So, Charles, when you heat a gas, the gas will expand. That does not mean the particles gain weight. That's not physically possible. What it means is they're moving faster and the distances between them are getting bigger. Okay, so volume over temperature equals a constant. Okay, a direct proportion. Okay, so volume, a little longer, temperature, boom, like that. Now, gotta tell you, I'm fibbing to you. This is in essence a lie, okay? It is not actually possible for this line to hit the origin. No matter what the temperature, even if I got it to absolute zero, the volume could not actually become truly zero. The particles would take up some volume. So let's redo it. Volume will swap on the axes. And it turns out that no matter what gas, and I'll just do two of them so it doesn't get too complicated, all gases converge on the same point on the y-axis when we do it this way. And that temperature is negative 273 degrees Celsius. And that is what we now call absolute zero. Okay? So, time for us to talk a little bit more about the particulate diagram. Okay? So, I'm going to shut up for 5 seconds, but you'll pause and actually go and take 2 minutes, and you're going to go watch somebody. I actually have no idea who this guy is, but he had a decent demo of it. You're going to go watch somebody dump some liquid nitrogen on a balloon. Okay? 5, 4, 3, 2, 1. Okay. Not the most exciting presentation of that in the world, but he didn't try to do anything creative. And I actually liked the way he stuck the balloon in a beaker, and then you could see that it fit into the beaker afterwards. I thought that was a good way of presenting it. Okay? Now, what we're going to do is we're going to play with volume and temperature, and we're going to keep pressure and moles constant. Keeping moles constant, very simple, tie off the balloon, don't let air in or out. Keeping pressure constant, no problem, we're just doing it in the room where pressure is pretty much constant. So we'll double the Kelvin temperature. Okay, over here in my 1 liter balloon, boom, boom, boom. We got these particles flying around. That's not a very good arrow. Sorry, drop that arrow. Got these particles flying around, pushing out, and at the same time, I have an equal balanced force on the outside pushing in. Now suddenly, I've doubled the temperature. Now, on the outside, I still have that exact same pressure that's pushing in. I'm keeping pressure constant. But since these particles are now going to be pushing with twice the energy outwards because I've doubled the temperature, that's going to cause the balloon to double in volume. Okay? They're moving faster. They're at a higher temperature. And remember, as I said before, I want you to think of temperature as molecular motion. Okay? All right, so this is actually a pretty cool concept here, okay? I think this was one of our better discoveries. The problem is Charles didn't actually make it. It was made by a guy named Joseph Gay-Lussac, and he allowed Charles to name it because Charles wasn't quite getting the recognition that Gay-Lussac kind of thought that he should have, okay? So Gay-Lussac originally was working with pressure and temperature, okay? Now imagine that volume and moles are constant, okay? And boom, 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 except we double the temperature, 2 times the temperature. These lines are going to be twice as long. So these arrows representing the particles flying around are now hitting the walls twice as often. The pressure is going to go up. It's going to increase. Okay? Now, next up here is a slow-mo video that another actually really great friend of mine named Tom Kunzelman did. And Tom is a college professor at a small school in Michigan. He started out as a high school teacher, and he, like myself, had a real love for chemical physics. So he went back, got his PhD in chemical physics, and ended up doing college teaching. And he has always stayed in the chemical education community, and he's become a pretty well-known guy on YouTube under the nickname of Tommy Technician. His real name is Tom Kunzelman. So watch this video that he has, a slow-mo video about can crushing. But then check out all the other stuff he has, because he's got some really good things that are available. Okay, and that brings us to the end of page number 4. But I am going to just ever so briefly jump us up to page number 5 to finish off that concept. And that's the combined gas law. See, it turns out that with that can crushing demo, we have to realize that there's more than one thing going on, because you can't control all the parameters, okay? And P1 V1 over T1 equals P2 V2 over T2. Now, the way I would really like to show this to you would be with a balloon demonstration like Boyle's Law. What I'd do is I would hand it to somebody in the front row, have them hold it, examine it. Then I'd put it into the bell jar. I'd pull the vacuum, let the balloon get bigger, put the air back in, let the balloon get smaller, open it up. Oh, it's warm. See, because I never actually let anybody handle the balloon that first day when it was just getting bigger and smaller. See, it turns out I didn't have it in the temperature bath, so there was actually no way to control the temperature, okay? So pressure, volume, and temperature are changing in that demo. And in that can crushing demo, got to understand that we're also allowing air to go in and out of that can, which is another big deal, okay? So you'd have moles involved in this also. Okay, so that finishes off that idea. All right, thanks for tuning in.